In this section, we begin discussing infinitely divisible distributions, and we will begin with the definition and some motivation. So first, the definition is as follows. A distribution P on the real line is called infinitely divisible if for any integer n greater or equal than 1, we can find a distribution Pn such that our distribution P is an n-fold convolution of Pn. Another way to say this in terms of random variables is that if you have a random variable with the distribution P, and then you take IID random variables x1, xn with the distribution Pn, then x will be equal in distribution to the sum of x1, xn. Because we know that the distribution of the sum of two independent random variables, it's just the convolution of their distributions. Okay, so that's the definition, and the motivation comes from the so-called Levy processes. So Levy processes will be processes xt indexed by t greater or equal than 0, such that at 0 they are equal to 0, and such that they satisfy the following properties. These properties are very similar to the properties in the definition of the Brownian motion, with one important difference. So the first property will be independence of the increments, which just means if you take a finite number of indices or finite number of these times, t1 up to some td for arbitrary d, and you look at the increments at time t1, so minus time 0 is just 0, and then between time t2 and time t1, and so on. Okay, these will be independent. Then the second property is what we call stationarity, which means that if you consider two indices, let's say s strictly less than t, then the increment of the process between times t and times s will be equal in distribution to the process at time t minus s. So in other words, the distribution of the increment only depends on the increment of the time. And the last property is continuity in probability, which means that when the index converges to another index, then the process converges in probability. And let me write this a little bit more explicitly by saying that when we look at the increment of the process between some time c plus h and time c, convergence in probability just means that for any strictly positive epsilon, this probability will go to 0 as this h goes to 0. So for Brownian motion, we had a stronger property, which was continuity almost surely, or continuity for each path. But here we require something weaker, namely continuity in probability. So we already know some classical examples such as a Gaussian distribution. By the stability property of Gaussian, they are obviously infinitely divisible. And on the side of the Levy processes, we have Brownian motion, which satisfies all these properties and whose increments have specifically Gaussian distributions. Now, we also know the classical stability property for Poisson, right? That the sum of Poissons is Poisson, where you just add up the mean, so this makes it also infinitely divisible. And at the end of this section, we will discuss the so-called compound Poisson processes. which can be viewed as a Levy process analog of the Poisson distribution in some sense. Now, another distribution which is infinitely divisible is the so-called gamma distribution with parameters alpha and beta, where alpha and beta are two positive parameters, right? And this distribution has density given by this formula, beta to the alpha over gamma function at alpha, x to the alpha minus 1, e to the minus beta x for positive x. And one can check that the convolution of two gamma distributions, when you keep parameter beta fixed, but you can change the parameter alpha, this will also give you a gamma distribution with parameter alpha 1 plus alpha 2 with the same beta. And this one can check directly just by using a convolution formula for the densities, or we'll leave it as an exercise at the end of this section, that a characteristic function of this distribution is given by 1 over 1 minus it over beta to the power alpha. And so we can see that when we take a product of such characteristic functions with the same beta, the alpha parameters will just add up, and of course this just corresponds to taking convolutions of those distributions. Now, another classical example is the so-called Cauchy distribution with parameter a, which is also positive. Right, and this distribution has the following density. So the density is given by a over pi squared x squared plus a squared for all x on the real line. And again, one can check that the convolution of such densities will give you density of the same form, or we'll leave this again as an exercise at the end of this section, that if you compute a characteristic function, it will be equal to e to the minus a absolute value of t. So the product of these characteristic functions is again of the same form, where parameter a adds up. So the sum of Cauchy is also Cauchy. Okay, and after we discuss some basic properties of infinitely divisible distributions, we will give a few more examples in this section, and then in the next section we will actually characterize characteristic functions of all infinitely divisible distributions. So it turns out that a characteristic function of an infinitely divisible distribution can never be equal to 0. And we'll prove this first, and for that we'll actually need the following simple technical lemma, which states that if you have any characteristic function, so let me write it like this, as expectation of e to the itx for some random variable x with distribution p on the real line, then 1 minus the real part of this characteristic function evaluated at 2t can be bounded by 4 times the same expression at time t. And moreover, if you write the absolute value instead of the real part squared, you have the same inequality. And this is really an elementary observation, where if you write this left-hand side, when you calculate the real part, and let me write it in terms of the integral with respect to the distribution, the real part of e to the itx will be, of course, cosine, and we want this at 2t. Okay, so that's the left-hand side, and then if I just use the formula for the double angle, I can write this as twice 1 minus cosine squared, which I will write as 1 minus cosine 1 plus cosine. Okay, and both factors in the integral are non-negative, and the second factor is bounded by 2, so that's where this 4 comes from, and we are left with 1 minus cosine tx. So this is again just a real part of the characteristic function at t. And for the second part, about the absolute values, of course, that just comes from the fact that absolute value squared is a characteristic function of some distribution. Namely, if you take two independent random variables from this distribution P, the characteristic function of their difference, so x1 minus x2, of course, by independence, you can write this as a characteristic function of x1 and then characteristic function of x2, which is the same characteristic function at time t, right? And of course, the second you can write as a conjugate of the characteristic function at t, and so that gives us exactly the absolute value squared. So an absolute value squared of a characteristic function is always a characteristic function, so our part 1 implies part 2 immediately because it's real. And so using this simple observation, we will prove this crucial lemma that we will need, that if we have an infinitely divisible distribution, and we'll just write it throughout the section, we'll abbreviate it by IDD. So if it's infinitely divisible distribution, then its characteristic function can never be equal to 0. So it's not equal to 0 for all t on the real line. And when we prove this, of course, it's more convenient to work with the real valued characteristic function. So we'll look at the absolute value of characteristic function squared, right? As we said, it is also a characteristic function. And so I want to apply the above observation in the second form. So 1 minus absolute value of characteristic function squared. And then we said that if you halve the parameter, so replace t by t over 2, you have to put a factor 4 in front. But then I'm just going to repeat this operation k times, and so 4 will come out k times, and then the parameter t will be halved k times, so it will be divided by 2 to the k. Right, so we have this kind of inequality just by repeated application of the above inequality. And I want to apply this inequality to the characteristic function fn of t of this distribution Pn, right? So fn of t will be a characteristic function of the distribution Pn that appears in the definition, right? Since P is infinitely divisible, P can be written as some Pn n-fold convolution. And so I want to apply this inequality to Fn. In other words, 1 minus this absolute value squared is bounded by 4 to the k, 1 minus the absolute value at t over 2 to the k squared. Right, and of course for absolute values, we can write this in terms of the original characteristic function f. Right, because from this equation here, the absolute value of fn is just the absolute value of f to the power 1 over n. Okay, so we can write it like this. Now it becomes clear why we wanted to halve the argument repeatedly, because the characteristic function at 0 is equal to 1, and the characteristic function is always continuous. So in particular, a characteristic function at t over 2 to the k, if you take k large enough, the parameter will be close to 0, and you can make this absolute value as close to 1 as you like. So this will be not equal to 0 for large enough k. Okay, so let's fix such particular parameter k. And then we will use the fact that since the characteristic function here, this parameter, is not equal to 0, when you take the power 2 over n, when n is getting large, this will go to 1, right, when n goes to infinity. In particular, we can take n so that the above bound is as small as we like, and let's say less than 1/2. Okay, so it proves that this expression on the left hand side is less than 1/2, or in other words, that this quantity is bigger than 1/2. And in particular, that means that fn of t is not equal to 0. And of course, f was just the nth power of this, so f of t is also not equal to 0. Okay, and this finishes the proof of this lemma. So we will use this fact that the characteristic function is non-zero in the following way. So let me state this as a remark. Okay, so the fact that our characteristic function is a continuous function of this parameter t, and in the case when its modulus is not equal to 0 for all t, this means that when you represent your characteristic function in polar coordinates as the modulus times e to the it argument, or this angle theta of t, if we also use the fact that characteristic function at 0 is equal to 1, we can start with this angle theta as a function of t at 0 to be equal to 0. And the fact that this modulus r is never equal to 0, and of course it's also continuous, means that you can divide both sides by r of t, and so e to the it theta will also be continuous. And so if we start with theta at 0 equal to 0, we have a unique continuous choice of this argument theta t. Okay, and we will call this particular polar coordinate representation of our characteristic function with this unique continuous choice of theta, in this case, a canonical representation. Okay, moreover, if our characteristic function f of t, it can be written as a power of some other characteristic function, like in the case of infinitely divisible distributions. Now this characteristic function fn will also be not equal to 0 for all t, and so we can also take this unique canonical representation of this characteristic function fn of t for some functions Rn and theta n. And of course, this relationship with characteristic function f means that Rn of t will be just the nth root of Rt, and theta n of t will be just theta of t divided by n. Okay, and so in other words, under the assumption that our characteristic function is not 0, we have this unique choice of parameters in this canonical representation for the nth root of the characteristic function. And so whenever we take the nth root for the infinitely divisible distributions, we'll always assume that this is the choice of the parameters. And next we'll discuss several operations on infinitely divisible distributions. Our first observation will be that a convolution of two infinitely divisible distributions is also infinitely divisible. Okay, and this is kind of an obvious observation because if you take a corresponding distribution Pn for this first one and for the second, of course the convolution of those will be the corresponding Pn for the convolution of these two distributions. So there is really nothing to prove here. Okay, our next observation will be actually much less trivial, and that's the fact that a limit of infinitely divisible distributions is also an infinitely divisible distribution. And to prove this, we will first notice that since this distribution pk is infinitely divisible, it can be written as an n-fold convolution of some distribution, let's say pkn. And let's take a characteristic function of this distribution pkn and denote it fkn. So in particular, fkn to the power n will be the characteristic function fk of this distribution pk. And since pk converges to p, characteristic functions also converge, right? So here f is a characteristic function of p. Now, because of this convergence, the absolute values also converge. And if I take the square, that will give us that the square of the modulus of characteristic function fkn converges to the modulus of f to the power 2 over n. And then we know that the square of the modulus of a characteristic function is also a characteristic function. And we also know that when characteristic functions converge, and the limit is continuous at 0, which obviously this is, it implies that this function here is also a characteristic function. And in particular, we just proved that we can represent the square of the modulus of our original characteristic function of f as the nth power of some characteristic function. So in other words, we just showed that this is a characteristic function of some infinitely divisible distribution. And by a lemma that we proved above, this implies that this characteristic function here is not equal to 0 for all t. So in particular, the modulus of our characteristic function of the distribution p is not equal to 0 for all t. Alright, so next let's look at this convergence of characteristic function fk to f. And now let's represent them in the polar coordinates in this canonical representation we discussed above. So we can write that fk of t, if we represent it as some modulus rk of t e to the I argument theta k of t, right? We know that this converges to f of t, and since we just proved that this f of t is never equal to 0, that means we can also represent this in a canonical way for some functions r and theta, where the choice of theta is continuous function that starts at 0. Okay, but let's also recall that whenever characteristic functions converge, they also converge uniformly on compacts. We had an exercise in one of the earlier chapters, I think it was in chapter 3, which shows this. And of course this implies that rk of t converges to r of t also uniformly on compacts. And if we take into account the fact that this function r of t is non-zero everywhere and also continuous, this means that in the above convergence of the characteristic functions, if we divide by the modulus on both sides, we get that e to the I theta k also converges to e to the I theta of t in the limit uniformly on compacts. And from here, it's an easy exercise, so I'm going to leave this as an exercise at the end of the section to show that this implies that theta k of t converges to theta of t for all t. Okay, of course, here we have to use that all these functions theta were chosen to be continuous and start at 0 at time 0. Okay, and using this information and uniform convergence, we can see that we must have this convergence. Okay, but once we have this, we can say that our characteristic function fkn above, which was just the nth root of the characteristic function fk that we can write as this modulus to the power 1 over n and e to the I theta k divided by n, as we discussed above. Right now we know that this will converge to r of t to the 1 over n, and theta converges to this corresponding theta of t in the limit, and this limit we can denote as some function fn of t. The fact that the left-hand side was a characteristic function implies that this limit, which is a continuous function equal to 1 at time 0, will also be a characteristic function. So in other words, we are able to write a characteristic function of our distribution p as the nth power of some function fn, or its nth root, which turned out to be a characteristic function. So in particular, it's a characteristic function of some distribution, let's say Pn, and of course this means that P is a n-fold convolution of this Pn, which proves what we want, namely that P is an infinitely divisible distribution. Okay, so this finishes the proof of this lemma. Okay, so this fact that infinitely divisible distributions are closed under taking limits will be very important to us, and one consequence of this will be the following result, which says that if we have some infinitely divisible distribution P and f of t is its characteristic function, then f of t to the power c for any positive c will be also a characteristic function of some infinitely divisible distribution. Okay, and of course the statement is obvious for rational c, right? Because we already know that taking a power of a characteristic function just corresponds to convolution, and so that will be an infinitely divisible distribution. And then of course the nth root will correspond to some infinitely divisible distribution, because if we take an nth root, as we discussed above, we can write this as a modulus of f to the 1 over n, e to the I, the argument, this canonical argument for the function f, divided by n. And then if we want to take a further root, or in other words represent this as a power of something, we can write this as 1 over, let's say, nk e to the I theta divided by nk to the power k. And this n times k root of the original function f is a characteristic function of some distribution with the parameter n times k. And so this function that we started with, which was a characteristic function of Pn, is written as the kth power of Pnk. So in particular, Pn is a k-fold convolution of this distribution Pnk. And so for rational choice of C, this just follows from the definition, and then by the previous theorem, when we take the limit m over n goes to arbitrary c, we have a convergence of characteristic functions. And so this implies that a function of this form will be a characteristic function of an infinitely divisible distribution as well. Okay, so this finishes the proof of this theorem. And so with all these tools, in the next video we will discuss Levy processes and give some more examples of infinitely divisible distributions.